Good morning, stats students. Let's go over your Unit 5 exam review together. All right, here we go. The National Directory of Magazines tracks the number of magazines published in the United States each year. An analysis of data from 1988 to 2007 gives the following computer output. The dates were recorded as years since 1988. Thus, the year 1988 was recorded as year 0. A residual plot not shown showed no pattern. All right, so a linear fit seems appropriate. What is the value of the slope of the least squares regression line? Interpret the slope in context of this situation. All right, so remember your slope is right here across from your indicated x value. So your slope is 325.39 over 1. Ew, I don't know why it's writing this. All right, and remember this is your change in y over your change in x. So for the slope, we can say every year the number of magazines published, the number of magazines published increases by 325.39. What is the value of the y-intercept? All right, so your y-intercept is next to the word constant. And remember, your y-intercept is when x is 0. So 0, 13,549.9. So at year 0, which is 1988, there were 13,549.9 magazines published. Predict the number of magazines published in the United States since 1999. All right, so our equation for line of best fit is y hat equals 325.39x plus 13,549.9. And since 1999, this is 11 years, so x would equal 11. So we're going to plug in 11 here. And we are going to get out 17,129.19 magazines produced. In 1989. This is what we would expect. Okay. What is the value of the correlation coefficient for number of magazines published in the U.S. in years since 1988? All right. So your correlation coefficient, we've got r squared right here is 0.848. So r is equal to the square root of 0.848, which would be 0.92086, so 921. And the interpretation would indicate that there is a strong positive linear relationship between x, which is a number of years since 1988, and y, which is the number of magazines published. All right. Number 1 down. All right, number 2. The heights in inches and weights in pounds of 6 male Labrador retrievers were measured. The height of a dog is measured at the shoulder. A linear regression analysis was done, and the residual plot is right here. Is a line an appropriate model to use for these data? What information tells you this? Okay, so we're going to look at our residual plot and see if it looks random. Now, we only have 6 points, so that's not a lot to go off of. But here's what we can look at. We see that r squared is 0.953, and so we can take the square root of that and determine that r is 0.976. So we have a high r value of 0.976 and a high r squared value of 0.953, and the residual plot looks random. Does not show any clear pattern. So it seems appropriate. So we'll say yes. It's kind of hard to determine when we have such a small number of data points, but since we don't have any clear pattern here, it seems okay, seems appropriate enough. Write an equation of the least squares regression line in context. Okay, so remember, my slope and my x value are here. My y-intercept is here. And I have to just read the context for my y value, which in this case is weight. So we can say that the weight hat is equal to 3.6956x, which is height, minus 13.430. All right, next problem. Dakota, a male Labrador, was one of the dogs measured for this study. His height is 23.5 inches. Find Dakota's predicted weight and Dakota's actual weight. Okay, so his height is 23.5 inches. So his predicted weight, we're going to use our line of best fit. So 3.6956 times 23.5 minus 13.430. And we will get a predicted weight out of 73.446 pounds. So there's a predicted weight. Now to find his actual weight, this is going to be a little bit more tricky. We're going to have to use our residual plot. So Dakota's male Labrador has a height of 23.5 inches, that's x. So we can come over on the residual plot and see this point right here corresponds to Dakota. And this has a residual value of 2.5. And so remember, your residuals are equal to observed minus expected equals the residuals. So in our case, our observed, we don't know what it is, or the actual, we don't know what it is, minus expected is 73.446 pounds, gave us a residual of 2.5. So when we solve, I'm sorry, this is not 2.5. This is my mistake. It's 1.5. My apologies. Sorry. $1.5. So when we add 73.446 over, we get that y is equal to 74.946. and that would be his actual weight. Okay. All right. As more miles are driven in a car, the resale value of the car generally declines. This is called depreciation. For a certain make and model of car, information is gathered on the resale price in dollars and the number of miles driven in thousands of miles. The scatter plot of price versus miles, the residual plot, and the least squares regression line is shown for this data. In addition, the scatter plot, residual plot, and accompanying best fits are shown for two other models using the common log. All right. So using Model 1, estimate a resale price for a car of this make and model, which has been driven 35,000 miles. Okay, so using Model 1, X is in thousands of miles, so we're going to plug in X equals 35. Because up here it says in thousands of miles. And we're going to use this equation right here for this problem part A. So here we go. We're going to say 29,784 minus 343.58x is going to be 35. And we're going to get out 17,758.7. So the resale price for a car, or I'm not going to say for the car, whatever, with 35,000 miles is estimated to be $17,758.70. All right, so that was using Model 1 because it told us to. Model 1 is not the most appropriate to use to compute and estimate resale price. Explain why it is not appropriate and determine whether Model 2 or 3 is better. All right, so why would we not choose Model 1? Well, if you notice, the R value is the lowest, okay? So Model 1 has the lowest R value. Okay, so there's one thing kind of stopping us. Okay, also, if we look at the residual plots, this has the most clear pattern of curvature. This is getting a little bit less. This one's the best, right? So there's also another indicator. The most pattern in its residual plot. Which would indicate it's not the best model. Okay, so Model 3 does seem to be the best. Highest R value. And most random residual plot. And that's all we really have to go off of here. Use the model you chose in Part B to estimate the resale price for a car of this make and model that has been driven 35,000 miles. So now we're going to plug in X equals 35 to our new, more appropriate plot. And we will get 43,254 minus 17,153. Okay, log of 35. Plug this into our calculator, and what do we get? we get 16,768.60. Okay. So the more accurate resale price for the car with 35,000 miles is estimated to be $16,768.60. All right. Moving on to problem 4. The problem of soil erosion is faced by farmers all over the world. The following data was from a study in Western India. All right, so we're looking at velocity versus erosion. So here we're going to go ahead and we are going to put velocity into list 1 as our x values and erosion into list 2 as our y values. And we are going to pull up a scatter plot of velocity, which is list 1, versus erosion, which is list 2. I'm going to give you guys a second to do that now. So pause your video and do that. Alrighty, and your scatter plot should look something like this. And our least squares regression line, how you're going to get that is you are going to go to Stat, Calc, Option 8, which is linear regression. And we're looking at list 1 versus list 2. And here's what your line should be. It should be y hat equals negative 281.9998 plus 19.85x. Okay, so calculate and interpret the r and r squared value. R is 0.903 and r squared is 0.8157. Remember, if you don't get your r and r squared value when you do this linear regression, make sure that your diagnostic is on. And you can get that by going to second catalog and turn the diagnostic on. All right, so let's interpret this. This tells me there is a strong, positive, linear, those are your 3 keywords, relationship between x, which is velocity, and y, which is erosion. All right, r squared, 81.57% of the variation in y, which is erosion, can be explained by the linear relationship with x, which is velocity. All right, very important that we know how to interpret these two values. Part D tells us to create a residual plot. All right, so here's what we've got going on here. List 1, we have x values. List 2, we have y values. List 3, we're going to compute those y hat values, all of our predicted values, by plugging in every single x value into our equation. And in list 4, I'm going to want to find those residuals, which is my y values minus my y hat values. And so list 4, I'm going to take list 2 and subtract list 3. And those will be my residuals. So I'm going to look at my residuals, which are in list 4, versus my original x values, which is my velocity in list 1. All right, I'm going to pause the video and give you guys a second to pull up the scatter plot now. Okay, and this is what your residual plot should look like. It says describe the distribution. All right, there definitely is some slight curvature occurring here. This little point is throwing it off, but otherwise we would have more of a clear pattern, okay? So there does seem to be some curvature in the residual plot. There does seem to be curvature or a pattern in the residual plot. Okay, which indicates there may be a better fit for the data. So this linear fit might not be working. All right, in part E, it says use a transformation of natural log of y on natural log of x to see if this is a better fit. All right, so in my list, I'm going to have list 1 as x, list 2 as y. I'm going to clear out list 3 from before and make it my natural log of x. And list 4, I'm going to clear out from before and make it my natural log of y because I don't need that anymore. And now I'm going to look at the natural log of velocity, my list 3, versus my natural log of erosion, my list 4, and see if it looks any more linear. So I'm going to give you guys a second to pull that up now. All right, so here is what your graph should look like. And we're going to calculate that least squares regression line again by, remember, going to stat calc linear regression. This is option number 8. The only thing is we get out this equation. Y hat equals negative 9.38 plus 4.58x. The only thing that you need to remember is that this isn't actually what we're looking at because these aren't just x and y values that I have plugged in here. I have the natural log of y and the natural log of x. My calculator can't take that into consideration, but I have to. So we need to write in that natural log. And in order to get rid of that natural log to give me a y hat equation, I need to raise both sides to the power of e. So my actual least squares regression line is y hat is equal to e to the negative 9.38 plus 4.58 natural log of x. This is the line that fits my original data that seems to have some slight curvature. All right, my r value is 0.9357. And my r squared is 0.8755. So here's how we interpret this. There is a strong positive, I'm going to say linear, relationship between the natural log of velocity and the natural log of erosion. Okay. And down here, 87.55% of the variation in y. Y is the natural log of erosion in this case. Can be explained by the linear relationship with the natural log of velocity. Things you absolutely must know. All right, create a residual plot of the transformed data, describe the distribution. All right, so I need to get my y hat value. So up here, in my list 5, I need to calculate my y hat values. So I'm going to take my equation, e to the negative 9.38 plus 4.58 natural log of list 1. And I'm going to plug every single x value into this equation. Be really careful with your parentheses here. You want to make sure that you place parentheses around the entire exponent so that we don't get any kind of miscalculations. Then in list 6, I want the residuals. And remember, residuals are y minus y hat. Y is in list 2. Minus predicted is in list 5. So when I look at my residual plot, I'm looking at my regular initial y values, x values, velocity, versus my residuals, which are in list 6. That's because we're looking at how far these points stray from the line on the original data, okay? I'm going to give you guys a second pause to complete the residual plot now. Okay, so here is what our residual plot looks like. It says describe the distribution. Okay. There definitely is a clear pattern. In the residual plot. Okay, there's no curvature, which is even worse, but there is a pattern, okay, indicating we still have not found the best linear fit. Okay, so we still have not found it. And honestly, I only gave you 2 options to look at now. So I gave you the original and the second transform data of natural log versus natural log. So we may not have found it. There's lots of other options that are out there, but we just aren't going to explore them all because that will take forever. So based off of the evidence we have, we are aware that we may not have the best fit in the world for our data, but out of the 2, which one is better? So we have 4 things to look at. First thing, the scatter plots, okay? So the transformed scatter plot does seem and appear slightly more linear than the original. It shows, you know, an increasing pattern. All right, second thing is my R values, okay? Well, second and third, my R and R squared values. My transformed data has a higher R and R squared values. And the last one is the residual plot, okay? So the residual plot doesn't seem much better. Okay, this indicates we have not found a very good fit. So we haven't found the best fit for our data, okay? But given the 2 options, the transform checks out here, and not really here, but the transform data does seem to be better, okay? It's a better fit given what we have. So this might happen. Like, it's not the best situation, but we're only looking at the options that we were given, and the transform data is better based off of all of the evidence that we have. So you want to make sure that you go through and support yourself 1, 2, 3, and 4 through all of these steps. All right, you guys. Hopefully this was helpful. If not, I will see you in office hours. Bye.